So we've been working with integration using partial fraction decomposition, and well, so the method works like having a complicated rational expression and split it into the sum or difference depending on the coefficients of simpler fractions, simpler partial fractions. Well, to begin with, let's look at this integral. When we analyze this integral, notice the degree in the numerator is larger than the degree in the denominator. This means that the rational expression in this case is improper. So what do we have to do in this case? Well, we will have to do the polynomial long division. Okay, so we're going to write x cubed plus x, or actually, check this out. Number one, notice how some of the terms are missing. In the numerator, we're missing the square term, and in the denominator, we're missing the linear term. So my advice, every time you have a polynomial long division in which some of the terms are missing, add placeholders. In this case, 0x squared plus x minus 3. And divide this by x squared plus 0x minus 4. And the reason we use these placeholders is so we can organize everything by its corresponding powers. So it doesn't look weird when we try to combine the terms together, that you are combining cubics with quadratics, and then that looks weird, and it's very easy to get stuck in a situation like that. Adding these placeholders will avoid those situations. Well, so to divide polynomial, what do we do? Well, we divide the leading term of the dividend by the leading term of the divisor. So number one, what's x cubed over x squared? X. Okay, let's put it on top of the corresponding term, x. Alright, not x squared. Now, I mean, it doesn't make a difference anyway, but it looks nicer, it's easy to read, it looks more organized. And then we're going to multiply x times every single term right here in the divisor. X times x cubed. X times x squared, x cubed. X times 0x, that's a 0x squared. X times 4, that's a 4. Now, every time we do this multiplication of every single term in the divisor, what do? We need to change the sign of what we obtain. So in this case, positive times a positive will be positive. We need to change it to a negative. Positive times a positive is positive. We change it to a negative. And positive times a negative, which is negative, we need to change it to a positive. Why do we do that? Because how many times does 3 go into 17? 5? 5 times 3. But what do we do here? Subtract to get the remainder, right? But in this case, what are we doing here? Positive times a positive, which is positive. We're subtracting it. We're essentially changing the sign, don't we? Mm-hmm. So we do the same with polynomials when we divide polynomials. And well, let's divide out or cancel out terms to simplify the division. And x plus 4x, that's a 5x minus 3. Drop the next term. Now, this is the first remainder of the division algorithm here. Now, we need to observe, we need to look at the degree of this remainder. If this remainder is of the same degree or higher than that of the divisor, we need to continue doing this polynomial long division. Otherwise, like in this case, well, the degree is 1. This degree is below the x squared. So in this case, we're done with the polynomial long division. So we may go back to the integral and write this rational exponent using our information from the polynomial long division in the form of quotient plus remainder over divisor. Coming back to the division, that's quotient plus remainder over divisor, and we write it as a mixed fraction back when we did it with numbers. With polynomials, it's the same thing. Quotient, which is x, plus remainder over divisor. Alright. And we may go about the integral right here. So this will be the integral of x dx plus the integral of 5x minus 3 over x squared minus 4 dx. And well, the integral of x dx, well, that's just a general power rule problem. Now this one is the one that we need to do using partial fraction decomposition. So let me focus on this integral. So that's the integral of x dx plus the integral, okay, x squared minus 4. Can we simplify that x squared minus 4? I mean, it's a quadratic. But is it a quadratic reducible or is a quadratic irreducible? It's reducible because we can factor it out as a product of two linear factors. In this case, using the difference of squares, x minus 2, x plus 2. Right? And in this case, we will split the integral x dx plus the integral of a over x minus 2 plus b over x plus 2 dx. Alright, so let's focus on this integral. So we need to find the constants a and b that actually split this integral, right? So we're going to set these two quantities equal to each other, equal to one another. That's going to be 5x plus minus 3 over x minus 2, x plus 2 equal to a over x minus 2 plus b over x plus 2. But again, you don't want to work with an equation this complicated, so simplify the equation, eliminate the denominators. We get that done by multiplying by the least common denominator, which in this case is the product x minus 2, x plus 2. So distributing over the left hand side, actually all of it cancels, leaving us with 5x minus 3 equal to, when we distribute over the right hand side for the first term, notice how the x minus 2's cancel, leaving us with a times x plus 2. When we do the second distribution over the second term, in this case the x plus 2's cancel, leaving us with the product between b and x minus 2. And this is our basic equation. And we will use this equation to figure out the values of a and b that split the integral into two partial fractions. Well, this one is going to take us back to the easy ones, because in this case we have a couple of options to zero out the terms. We can find a clever value to zero out the a term to find b, and we can easily find a clever value for x to zero out the b term, so we can cancel a. Any ideas of what those values are? 2 and negative 2. So for x equals negative 2, we're going to do so 5 times negative 2 minus 3, 8 times negative 2 plus 2, plus b times negative 2 minus 2. So that's 5 times negative 2, that's a negative 10, minus 3, that's a negative 13, and cancel. And negative 2 minus 2, isn't that a negative 4? Negative 4b, and b is then 13 over 4. So that's one. So you guys say the other value should be positive 2, right? Let's go ahead and do that one. Okay, so 5 times 2 minus 3 equals a times 2 plus 2 plus b times 2 minus 2. Cancel this to 0. 2 plus 2 equals to 4a, and 5 times 2, which is 10, and then 10 minus 3, isn't that a 7? A equals 7/4. Alright? Yes, this one wasn't any of those weird ones, right? In which we needed to come up with another value of x, any random value of x, because there was no way to get those clever values just as first glance. So let me go back to the integral. I'm going to write the whole thing, the integral of x dx, and then plus the integral of 7/4 over x minus 2 dx plus the integral of 13/4 over x plus 2 dx. Okay, the first integral, the integral of x dx, just use the general power rule. That's simply x squared over 2. And well, in this case, we are integrating dx over x minus 2 and dx over x plus 2. No need to show U substitution because look at the coefficient of x. It's just 1. Isn't that going to be a couple of ln rules here? So that's 7/4 ln of x minus 2, absolute value by the way, plus 13/4 ln of x plus 2 plus c. Final answer. So this one wasn't very crazy again. Well, the difference for this exercise in comparison with the previous one was the fact that we started with an improper fraction and we needed to do the polynomial long division. Then we do this. All right. The next one, however, I was eager to get to this one. The integral of x cubed plus x squared divided by the quantity x squared plus 4 squared. Well, number one, let's look at this integral. Number one, the rational expression is proper. Degree 3 in the numerator and essentially degree 4 in the denominator. So we're good. Let's look at the factors in the denominator. So we have an x squared plus 4. How would you classify that factor? It's quadratic, number one, and then, but quadratic, what kind of quadratic? Irreducible, right? Can we factor that over the integers? Even if you try and solve the equation, x squared plus 4 equals to 0, check what you get, -4. Oh, that's a square root, plus or minus -4. Plus or minus 2i. No, we don't want complex numbers. So in this case, we're going to treat this like a quadratic irreducible. So this will be a over x squared plus 4. Oh, not just a. Isn't it ax plus b? Because it's a quadratic. A quadratic corresponds 1 degree less in the numerator. If we had a cubic in the denominator, a cubic irreducible, it would have corresponded a quadratic like we did last time. And plus cx plus d over x squared plus 4 quantity squared. If this power in this case were a 4, we would have gone all the way to ex plus f, gx plus h to the third and to the fourth. But no, we're not going to go that far, all right? In fact, actually this power 2 would be more than enough. All right. So let's find the constants in this case, a, b, c, and d, that split this into partial fractions. So number one, we set these two quantities together to come up with an equation. X cubed plus x squared over x squared plus 4 quantity squared equals to ax plus b, x squared plus 4 plus cx plus d over x squared plus 4 quantity squared. But again, this equation is kind of crazy, it's kind of complicated. You might want to simplify by multiplying both sides by the least common denominator. And that has to be a power of x squared plus 4. Powerful enough not just to divide out the x squared plus 4, but also to divide out the x squared plus 4 squared. And that's actually our guy here to get the job done. Okay, you know the drill for this. Distribute, distribute, distribute. What happens? Cancel both of this, and that's going to leave us with x cubed plus x squared equals to, when we distribute x squared plus 4 squared over the first term on the right hand side of the equation, essentially we have an invisible power 1, and 2 minus 1, that's going to leave us with 1 power of x squared plus 4 ax plus b, x squared plus 4. And when we distribute over here, both powers of x squared plus 4 get canceled out, leaving us with cx plus d. And here is where the fun begins. Oh, this is number 1, our basic equation. Alright? Here is where we will have to find out those clever values that zero out some of the terms, so we can find one of the unknowns, whether A, B, C, or D. All right, can we think of something here? Zero. What happens with 0? Well, yes, the A goes away with 0. The C goes away. However, I'm left with B and A, with B and D. And the idea is to be left with only one letter every time we try to find one of those letter values. So, fortunately, well, 0 is not going to work. Negative 2, so negative 2 squared, that's going to be 4 plus 4. Well, we want to zero out the whole term. It's a trap here, right? However, we're going to go a different approach for this particular example. We're going to go over an approach called the method of undetermined coefficient. And this method is very important. It's great to get used to this method because you're going to use it in your future courses, such as differential equations, when you have to solve differential equations with a lot of polynomials, exponentials, and sines, and we need to find some unknown coefficients. And in this case, clever values is not going to work. So what are we going to do here? I'm going to distribute, 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 distribute. X squared, that's not the color. X squared plus, x cubed plus x squared equals ax times x squared, isn't that an ax cubed? Ax times 4, 4ax, and then b times x squared, that's bx squared, and b times 4, that's 4b. So that's the distribution or the foiling for the first term. Well, there's nothing else to do for the other two terms. So, what are we going to do instead of the clever values? So for the method of undetermined coefficients, we need to write everything in terms of powers and have those coefficients in terms in terms of A, B, C, and D. Whatever letters we have. So, what do we do in this case? I'm going to draw 3 bars for cubics, 2 bars for quadratics, 1 bar for linears, and just a wiggle for constant terms. All right. And well, what I'm doing here is some sort of a bookkeeping to have everything together in terms of powers. So. Don't forget about the left hand side for a second. Let's focus on the right hand side. Okay, cubics. It looks like we only have one term containing a cubic, right? So just ax cubed. Quadratics. We only have one quadratic term. So be it. What about linear terms? Oh, for linear, we have a couple of terms. So that means 4a plus c. You see what I'm doing here? I'm factoring out the x on the corresponding linear terms. If we distribute x over 4a and c, that's going to give us back this 4ax and cx. And then from here, so I'm done with the linear ones. What about constant terms? So constant terms, just group these two. 4b plus d. What are we going to do with this equation? Well, let's go back to the left hand side of the equation. What do we have? X cubed plus x squared. On the right hand side we have x cubed, x squared, x to the first, and a constant term, basically an x to the 0 if you will, right? No need to write that x to the 0. I just wrote it real quick so you can see the pattern of descending powers in this case. Well, so we want to have every single term on the left hand side. X cubed plus x squared, and it looks like this x cubed plus x squared is missing two terms. It's missing the x to the first power, and it's missing the constant term in this case. Well, it's not that they're missing. They're there. They're there in spirit. Let's summon their spirits by adding these placeholders. Right? Do we agree that 0x plus 0 is just the same? But the reason we want to place those to put those placeholders, oh, that's an invisible one, the coefficient. So the method of undetermined coefficients relies on equating coefficients, and this is what we're going to do. The coefficient of x cubed has to be equal to the coefficient of x cubed. Why? Because this is an equation, isn't it? Well, so 1 equals to a, 1 equals to b. The coefficient of x, this whole madness here, has to be equals to 0. And the constant term right here, this whole madness, has to be equal to 4b plus d. From here, we are going to write a system of equations. In some cases, the system of equations can go really crazy, like 4 equations for unknowns, 5 equations, 5 unknowns. But I mean, if you were doing this for homework, you can use your calculator using the matrix mode. So I'm going to set up a system of equations. So by equating coefficients, we get that a equals to 1. We'll also get that b equals to 1. Then we get that for a, for the coefficient of x to the first power, 4a plus c equals to the coefficient on the left hand side, which is 0. And last but not least, the constant term 4b plus d equals to this placeholder, which is 0 also. So that's our system of equations for equations, but not for unknowns. In this case, it's only 2 unknowns, which is great because we can solve the 2 equations to find c and d using the information from these 2, because a equals 1 and b equals 1. Yes?
Is it possible to get to this stage and then we don't see a possible solution with those equations?
No, these equations must have solution, and in fact, it has to be a unique solution, not one of those crazy ones that lead to no solution or infinitely many solutions. If you get one of those 2 cases, most likely there was some silly mistake in the process before getting this equation. So I would double check your procedure. So let's find the value of c. So we can find the value of c by plugging in a equals to 1 over here. So 4 times 1 plus c equals to 0. That means c equals to negative 4. And nope, this one. And yeah. For the next equation, we will plug in b equals to 1 over here to get, oh come on, 4 times b, which is 1, plus d equals to 0, that is d equals to negative 4. And in this case, I'm just highlighting just so you can see where are these highlights coming from, or why are we plugging in one value or the other, especially because, well, both a and b are equal to 1. If they were different numbers, we would see the difference here, right? So we got the coefficients a, b, c, and d. We may go back to the integral. By the way, where's the integral? It's above. Okay. I'm going to continue the integral over here. So coming back to put the coefficients a, b, and c, we're going to get the integral of x plus 1, because this is 1 and 1. A and b are 0. That's basically ax plus b, 1x plus 1, over x squared plus 1, 4 rather, dx, well, not the dx yet, plus negative 4x minus 4 over x squared plus 4, quantity squared, dx. Okay, let me zoom it out so you can see the coefficients. Ax plus b, where a and b are 1, 1 and 1, and cx plus d, and c is negative 4, and this also negative 4. You can see the negative 4 here and the other negative 4 there. Alright, let's go about these integrals. Number 1, let's try the simplest possible. Can we do U substitution for the first integral here, x squared plus 4? So set u equals x squared plus 4. The derivative du will be 2x. Well, the problem here is that we have an x plus 1, not just an x. So in this case, we need to split the integral into 2. In fact, we're going to split these 2 integrals into 4 integrals. Alright, each integral will take a particular approach. So that's going to be the integral of x. No, that's not going to be enough space. I need a lot of space. So that's going to be the integral of x over x squared plus 4 dx, plus the integral of 1 over x squared plus 4 dx, and well, plus negative 4x, that's actually minus 4 integral of x over x squared plus 4 dx, and last but not least, minus 4 times the integral of dx over x squared plus 4 quantity squared. Yes, this one. Okay, let's label them. 1, 2, 3, 4. Let's do one integral at a time. When I look at each integral, I know the third and the fourth integrals have a coefficient of 4 in the front. I'm going to skip that coefficient and I'm just going to include it at the end when I put all the results. So let's go about the first integral. So for the first integral, that's the integral of x over x squared plus 4 with respect to x. This one, it's just a U substitution. U equals x, du equals x squared plus 4. Du equals to x dx, which means x dx equals 1/2 du. So we're ready to do U substitution on the first integral. Let's go about it. Number 1, x dx becomes 1/2 du, and x squared plus 4 becomes a u. Well, isn't this just a 1/2 times the integral of du over u? What's the integral of du over u again? Absolute value of u. And going back, substitute for this, well, that's 1/2 ln of x squared plus 4. But do we really need absolute value bars here? No, not for this particular one. And I'm not going to write the plus c once I put everything together. Number 2, the second integral. That's the integral of x squared plus 4 in the denominator of 1 with respect to x. Can we use U substitution for this integral? No, not. I mean, a u to u setup will come into play though. However, not the way we were thinking in this case, like in the previous case. Because if we do, well, I'm not going to write the setup again. This same setup, well, we're missing a factor of x multiplying with the dx, so the u du works. Any ideas on how this integral is going to go about?
By parts?
Not by parts. the arctangent, the inverse tangent rule. So my advice is quantity squared plus quantity squared. That means what quantity squared equals x squared? What quantity squared equals 4? So that means u equals x, du equals dx, and a equals to 2. This integral becomes of the form 1 over u squared plus a squared du, which happens to be 1 over a arctan u over a, where a is just 2 and u equals x, and again u equals a. So I do this setup again because just in case you get some different integral, like in this case, what if we got the integral of 9x squared plus 4? The u would have been not just x but rather 3x. Take the u, that would have been 3dx, which means dx equals 1/3 du, so we would need a correction factor in this case. Okay, so that's the second integral. Let's look at the third integral. Integral number 3. That's the integral of what was that? X over x squared plus 4 quantity squared. I know there was a negative 4 in front of that integral, but again I'm gonna put it at the end when I put all the results together. So it looks like this setup right here is going to work because if we set u equals x squared plus 4 du to x dx, and again x dx equals 1/2 du. Alright, so x dx is 1/2, and x squared plus 4, isn't that a u squared? So there's a couple of things I would like to do about this integral. Number one, I'm going to take that coefficient of a half outside of the integral, and this u to the second power, well, we cannot integrate it while it's in the denominator, so we need to move it to the numerator with negative exponent. Alright, so integrating this using the general power rule, that's 1/2 u to the, okay, negative 2 plus 1, isn't that a negative 1 over negative 1? And well, let's clean this up. Number one, positive over negative is negative, and u to the negative 1, send it to the denominator as 2u, which is negative 1 over 2 times u, which is x squared plus 4. So score on number 3. How about number 4? Let's have a look. Let's write it down. This one is going to be the fun one. Number 4. That's the integral of, no, the other color. The integral of x squared plus 4, quantity squared in the denominator of 1 with respect x. Can we do U substitution? We're missing one factor of x, so we can't. Can we do the arctan rule, x squared plus 4, like we did for integral number 2? We can't because we have a power 2 here. What are we going to do here? Trigonometric substitution we're going to do here. But wait a minute, isn't this integral doesn't have any radicals, so we can do this trigonometric substitution. But with some magic touches here, we're going to make this look like radicals. Do we agree that the number 2, the exponent right here, x squared plus 4, isn't it the same as 4 divided by 2? Yes? And that's a rational exponent for which the denominator of the rational exponent indicates the index of the radical, and we got a radical function here. And the whole thing to the 4th power. And I know it looks ugly, it's not that bad, you'll see. Well, there's a couple of things that we need to check when it comes to trigonometric substitution. Number 1, do we have? A sum of squares inside of the radical or a difference of squares? Sum of squares. This means, okay, this is u equals x. Well, this is actually goes to x, and that's actually going to go to 2. Well, in this case, what do these two quantities represent for the triangle? The two sides, right? Side and side. Okay. Right triangle. And well, side, well, you have a couple of options to set it up. However, when we cover trigonometric substitution, I recommend it to have the variable to be the opposite and the constant to be the adjacent. No need to do the Pythagorean theorem because ultimately you're going to get to the radical for the hypotenuse. Right? Now, let's, in this case, find a substitution for the radical and a substitution for the dx. So, we need to use a ratio with the quantity that we have in our triangle. And, well, number one, for the radical, we have a couple of options. Radical over 2 and radical over x. Which of the two is the simplest of the two? Over 2. The radical over 2. And what trigonometric functions? I heard secant somewhere. That is correct. That means square root of x squared plus 4 equals to 2 secant theta. Again, doing this ratio involving the radical, it's going to save us from the 7 steps, 6 or 7. Remember we discussed that? Yeah. Alright? Let's find now a substitution for dx. Well, where is dx coming from? Isn't it coming from differentiating x? So we need a quotient involving the x, and we have a couple of options. X over radical, x over 2. How about x over 2? That's a lot better. And what trigonometric function is that? Tangent. That means x equals to tangent theta. And from here, we're going to differentiate both sides. And we have all the ingredients for the substitution. Alright. Secant, yeah, that's what I meant. So, let's take this problem in the world of x to the world of theta, solve it in the world of theta, and then go back to the world of x. That's the integral of the radical, which happens to be 2 secant, the whole thing to the 4 power. And it looks ugly, I know, but trust me, this one is going to simplify sort of nicely. Well, number one, let me simplify the denominator, but don't compute the 2 to the 4 itself. Leave it as 2 to the 4th. I know that's what's that, 16, right? On the one hand, we can divide out 2 powers of secant with 4 to leave us with 2 of them. Alright? On the other hand, 1 factor of 2 divides out with 1 out of the 4 to leave us with 3. We may now simplify this. Now, what's 2 to the 3rd power? Isn't that 8? And secant squared. Alright, so this is, okay, with this 8, you might want to take it out of the integral as 1/8. And can we integrate secant squared while it's in the denominator? If it were in the numerator, we would have gone all the way to tangent in one step, alright? However, we need to write this secant squared in the numerator as cosine squared. What do we have here? Powers of trigonometric functions, and in particular we have an even power of cosine. Had we had a sine multiplying with the d theta, we would have been able to use u equals cosine and du negative sine and do all the necessary adjustments. However, it's not the case. Lucky for us, we already went through the process of integrating trigonometric functions and all the identities that we use and all the tricks. So we have an even power. We can use the power reduction formula or half angle. That's 1/2, 1 plus cosine, and it duplicates the angle every time we use this identity. So two things here in one shot. 1/8 times 1/2. Isn't that a 1/16? And then at the same time, I'm going to split this into two integrals. Number one, the integral of 1 times d theta, which is d theta, plus 1/16, the integral of cosine 2 theta d theta. So let's see. What's next? Integrate 1/16, integral of not integral, that's just theta, and 1/, what's the integral of cosine again? Sine. Notice the space. I'm leaving here for the correction factor, that's 1/2, and simplify 1/16 theta plus 1/32 sine 2 theta. So we're done solving the problem in the world of theta right here. Alright? We need to go back to the original world, to the world of x. Okay, so we need to back substitute for theta from our substitutions here. We can do this using this equation here. Solve for theta, that's equal to arc tangent of x/2. But in this case, notice the double angle here. The setup that we did for this integral calls for single theta, single angles, not double angles, not quintuple angles, not millions angles, right? So we need to use another trigonometric identity here. How about in this case the double angle identity for sine? That's isn't that 2 sine cosine? Well, let's divide out the 2/32. That's 1/16 sine theta cosine theta, and we're good to go and do the back substitution for if we go back to the world of x. Number one, theta equals arctan of x/2 plus 1/16 times sine. Okay, sine for our triangle. Sine, which is opposite over hypotenuse, that's x over the radical. Agreed? Okay, so that's x over the radical, x squared, what's that? X squared plus 4. Times cosine. Go back to the triangle. Cosine, which is adjacent over hypotenuse, which is the constant over the radical. Let's simplify this one. Okay, 1/16 arctan x/2. Okay, 2/16, that's 1/8 plus 1/8, and then x times 1, that's an x in the numerator. And what happens when we multiply a radical expression with itself? Cancel the radical, just write down the expression inside of the radical, that is x squared plus 4. But how about instead we write this as a 8 in the denominator. Let me put this together. So that's the integral, the fourth integral. All right.